Okay, I'm going to explain to you two different versions of answers to the same question. The first version has got the correct physics. The second version has the wrong physics, but the second version is the answer that Cambridge expects from you. Okay, let me start with the first version, which has the correct physics. So in a transformer, we apply a sinusoidal voltage to the primary coil. This will produce a sinusoidal magnetic flux in the iron core. So both the primary and secondary coils will be experiencing a changing magnetic flux linkage. Therefore, there's going to be induced EMFs in both the primary and secondary coil. So there's the induced EMF in the primary coil, EP. And there's the induced EMF in the secondary coil called ES. In an ideal transformer, the coils have negligible resistance. So the induced EMF across this coil is also the terminal potential difference across the secondary coil. So the secondary voltage Vs is basically equals to the induced EMF in the secondary coil. So I'm going to write here ES is equals to Vs. Likewise, on the primary coil, if the resistance is negligible, then the induced EMF must match the primary voltage exactly. So I'm going to write here Vp is equals to EP. Let me now talk about the phase relationships between the magnetic flux and all these voltages here. According to Faraday's law, the induced EMFs is equals to the rates of change of magnetic flux linkage. Now we come to a very crucial point. Because of this iron core, whatever flux that's produced by the primary coil is linked completely to the secondary coil. There is no flux leakage. So whatever flux experienced by the primary coil is also the flux that's experienced by the secondary coil. So it's the same magnetic flux that goes into this equation here. Okay, let's say the magnetic flux is a sinusoidal graph. When you differentiate a sine, you get a cosine. So if phi is sine, then EP and VP should be cosine. So VP's graph should look like this. Now, some people might point out to you that the induced EMF in the primary coil is actually a back EMF that opposes the applied primary voltage. And they are right. So instead of VP equals to EP, it should have been VP equals to negative EP. And some of you could have been asking, what about the negative sign here? If this is sine, shouldn't EP and VP be negative cosine? So I have ignored all these negative signs to keep things simple. Anyway, in practice, you can flip the graph simply by winding the coils in the other direction. For example, instead of clockwise, you wind it anti-clockwise and you flip the graph. For that reason, I'm going to ignore these negative signs. The crucial thing is, since there's this sine cosine thing, the primary voltage and the magnetic flux cannot be in phase. There must be a quarter cycle phase difference between them. Alright? What about the secondary coils? You can see that the secondary coils induced EMF and voltages are also from the same magnetic flux. So Vs and Vp should have the exact same waveform. Alright? Now let me move on to the second version, which is the version that Cambridge expects you to write. And the version goes like this. Now, since it's the primary voltage that produces the primary current, that produces the magnetic flux, Vp should be in phase with the magnetic flux. I repeat, since it's Vp that produces Ip that produces the magnetic flux, Vp, Ip, and the magnetic flux should all be in phase. The induced EMF in the secondary coil is induced off the magnetic flux. So there must be a quarter cycle phase difference between them, which means Vs and Vp are out of phase by a quarter of a cycle. I'm sure you're very confused now. You want to ask me, so which version am I supposed to write if I get such an exam question? So my advice is to write the version that you understand better. So I'm going to very quickly run through the two versions again and see which one makes more sense to you, Okay, the first version, which is the correct physics, is that both the coils seize the exact same flux. So by Faraday's law, the induced EMFs in both the primary and the secondary should both be off by a quarter of a cycle compared to the magnetic flux. And EP is Vp, Es is Vs. So by Faraday's law, both Vp and Vs should be off by a quarter of a cycle with respect to the magnetic flux, which means both of them should be in phase. Or they could be completely out of phase if you decide to wind the coil the other way around. But they cannot be in phase with the magnetic flux, these two voltages. The second version says that because Vp is the one that produced the magnetic flux, it should be in phase with the magnetic flux. But Faraday's law says that the secondary voltage is off by a quarter of a cycle with respect to the magnetic flux. So since Vp is in phase with magnetic flux, but Vs is off by a quarter of a cycle with the magnetic flux, it means Vp and Vs should be off by a quarter of a cycle with each other. Okay? In both versions, there's agreement that due to Faraday's law, the secondary voltage and the magnetic flux are off by a quarter of a cycle. The difference between the two versions is the first version says Vp and magnetic flux are out of phase by a quarter of a cycle also, whereas the second version says that the primary voltage and the magnetic flux are in phase. What is wrong with the second version is it totally ignores the induced EMF in the primary coil. Arguably, the induction of EMF in the primary coil, which is often called self-induction, is not in the A-level syllabus. That's probably why Cambridge expects you to write the second version as the answer. But then on the other hand, the phenomena of the induced EMF in the primary coil is key to deriving the turn ratio formula. That's the ratio of the voltages in the two coils is related to the ratio of the number of turns in the two coils. That's why, as I said, just write the version that you understand better. Alright? If you write the second version, Cambridge will give you full marks. If you write the first version, if you explain your reasoning clearly, I'm sure Cambridge must award you full marks as well. Okay, I hope I've cleared the confusion. Ta-ta!